Hello, everyone. My name is Ioanna Kriekouki, and I'm a co-tutel PhD student of TIMA, STMicroelectronics, and Institut Quantique in Sherbrooke in Canada, where I am right now. And today I'm going to present to you my work on an industrial approach to silicon qubit architectures. I will start by giving you the main motivation of my domain, and I will continue with the cryogenic capabilities of FD-SOI technology. And I will finish with the fabrication of quantum dots on FD-SOI platforms for spin qubit applications. So why do we care about quantum computers? What could we do with them? Quantum computers harness the phenomena of quantum mechanics, and they could revolutionize the way we work in many domains today. For example, they could improve the efficiency of drug design and discovery, or they could accelerate the development of new chemicals and materials. But okay, let's be honest, it's very difficult to make quantum computers. And why so? Let's see the requirements for building one. First, let's think of a classical computer. What is its fundamental unit? It's the bit. It's quantum analog. A quantum computer processes quantum information using quantum bits, or qubits for short. Classical computers work with transistors, as you know. And just like classical transistors have different types, with the most important ones, the BJT and the MOSFET, there are several different qubit systems. Three of the most important. I'm sorry, someone has this microphone on. Did you try to say something, or was it? Okay, I'll continue. Three of the most important ones are the following. Superconducting circuits, with IBM and Google having invested in this technology, silicon spin, with Intel having invested in this technology, and trapped ions, with Honeywell having invested in this technology. Comparing to classical bits, qubits have higher error rates. As you know, classical information encoded as one, which means current flowing through the transistor, is very unlikely to decohere and change to zero, which means no current. Decoherence, however, is a problem in qubits. Thus, qubits have errors, but we can use a scheme to correct these errors. However, there is a price to pay for this, because this scheme requires a large number of qubits. Also, for computation, of course, we need more qubits that can communicate to each other, and we need a scalable system. With standard semiconductor technology, billions of transistors can be integrated on a single chip, and this is one of the main motivations for silicon spin qubits. Indeed, silicon is a very promising technology for quantum computing. It's a material that we know how it works from classical computers, and as silicon qubit platforms are fabricated using the same standard microelectronics technology as classical transistors, we could harness all the advantages of this industry, and we can envision integration of qubits with their control electronics and billions of qubits on a single chip. Finally, silicon provides extremely coherent qubits that work at higher temperatures than other competitor technologies, which require a deep cryogenic environment at almost absolute zero. The qubit approach that my group is focused on is electron spin in silicon quantum dots. A qubit can be any two-level system, that can encode quantum information at the states 0 and 1. So we use the two states of a spin of an electron as a qubit. But how can we manipulate a single electron? We confine it in a small region that's called a quantum dot. And this proposal, this approach, it was first proposed by Loss and DiVincenzo in 1998. And you can see the proposed qubit architecture in the picture here. The confinement is provided by electrostatic gates on nanofabricated structures, the quantum dots. Then, in order to have our two desired spin states, we need to apply an external magnetic field, and we're ready to manipulate our qubits and perform quantum computation sequences by using local magnetic fields applied with micromagnets, for example. So the first step towards electron spin qubits in silicon is a fabrication of reliable quantum dots with no defects. For this reason, my project is focused on the implementation of quantum dots with entirely industrial methods and techniques. This project is based on a partnership gathering people working on silicon qubits as experts in electrical engineering and specialists in mass production, fabrication, and packaging. You can see here all the people involved in the results that I will present today. Our devices are designed and fabricated using STMicroelectronics 28 nanometer, ultra thin body and buried oxide, fully depleted silicon-on-insulator technology. Here you can see a side cut of such a transistor, MOSFET. It consists of an ultra thin silicon body. And in order to induce a current between the source and the drain, we activate the channel by polarizing the transistor gate, which sits on a thin gate oxide. A unique feature of FD-SOI is that thanks to an ultra-thin buried oxide layer, we can also activate the channel from underneath by polarizing the backgate, and if designed properly, we can even have independent access to each device's backgate. So this characteristic adds a lot of flexibility to the operations of our quantum device, and also a third dimension we are less used to. So for FD-SOI so far, it has demonstrated unique characteristics, such as reduced leakage current, back bias control, better electrostatic control over the channel, high yield, low power consumption, which is very important for integration applications. And beyond that, variations of commercial FD-SOI have been used to demonstrate quantum dot and qubit capabilities. Indeed, the first multi-project wafer test structure that my group fabricated allowed us to demonstrate some of these features. Here is a top view of the structure. Let's neglect the side gates for the moment. You can see that it looks like a modified standard FD-SOI MOSFET. It consists of 4 terminals, the source, drain, front, and back gates. And this device was designed to investigate cryogenic behavior of the technology, and it was operated as a transistor at low temperatures. Reproducible key parameters were demonstrated, such as voltage threshold with a small variation, and also compared to room temperature measurements. Oh, I'm sorry. Carrier mobility and subthreshold swing appear to be improved at 1.5 Kelvin. This means that we can have reliable FD-SOI electronics at low temperature, setting the way towards integration. And now that we know that STMicroelectronics FD-SOI technology is functional at such low temperatures, the next step is to fabricate and investigate the quantum dot device. Here you can see a top view of the first MPW test structure designed to host quantum dots that my group designed, and it was based on the split gate device from Rochette's paper. The device is similar to the one that we just saw, but it has an additional electrode, the dot gate, which is yellow in this schematic. And let's see what we can do with it. Our drain is grounded and our source is polarized appropriately. So by applying positive voltage on the two parts of the front gate, we attract electrons from the source. And as we saw before at Loss and DiVincenzo's proposal, we need isolated and confined electrons in a well-defined region, our quantum dot. So by applying positive voltage on the dot gate, we attract electrons, which are under the front gate, and we form our quantum dot in the center of the device, as you can see here. Then an electron from the source can tunnel through the quantum dot to the drain. The movement of this electron contributes to the current induced in the device, and which we measured. We measured the current in the channel. While keeping the side gates grounded, we apply the appropriate voltages on the rest of the gates, and transport is induced in the channel. And here we are. We measure the current, and you can see that it's not the typical IV characteristics of a transistor anymore. But, however, electronic transport was only possible when exceeding the technology's standard voltage limit, which is 1.8 volts, risking to damage the device, and we had to stop. However, since the side gates are not deposited on the sensitive gate oxide, they can be pushed much further. And indeed, for a fixed voltage lower than 1.8 volt, on the front gates and the dot gate, starting at around 8 volt on the side gates, we can see these oscillations appear while measuring the current in the channel, indicating electronic transfer in quantum dots. And I'm sorry, I don't have the time to explain what are these oscillations and something else called Coulomb diamonds, but it's the signature of quantum dots in our device. So for a fixed voltage applied on the front and side gates, we swept the bias voltage while stepping the voltage applied on the dot gate, and we measure the current in the channel again, and voila. Coulomb diamonds were observed, indicating the formation of quantum dots in our platform. However, this device had larger dimensions than the ones that we initially wanted because of design rules restrictions. And for this reason, the quantum dots that we want to have, as I showed you before, they are not the same as the ones that we actually had, but they are formed here and here instead. And now the trajectory of our electron traveling from source to drain is this one. So it's critical to design smaller features. And here is where I come in. On the first generation of my multi-project wafer devices, I designed and fabricated 3 different types of quantum dot. test structures with reduced dimensions. On the second generation, I designed two different types of single quantum dot devices, 3 different quantum dot linear arrays, and a co-integrated device with a charge sensor to detect electrons coming in and out of the quantum dot, with vertical access to the dot gates, as you can see in the picture here. I'm currently measuring these devices, and I'm also designing the third generation of quantum dot data structures. So I have presented to you today that the FD-SOI technology is a promising platform for quantum computing with spin qubits, showing great promises for scale-up and co-integration. And we have demonstrated that the technology is functional at cryogenic temperatures, and that we can indeed form electrostatic quantum dots with this platform. Right now, we're working on reducing the device critical dimensions, and we're also working on the co-integration with the control blocks. Thank you very much for listening.
Thank you very much, Ioanna, for your very nice presentation. Are there any questions for Ioanna from the audience? I would have a question, curiosity more than, because it's a little bit out of the of my knowledge scale. Can you tell us a little bit about the scaling of these devices or maybe the opposite, how many can we integrate and how large can we get to the system?
Yeah, because of confidentiality reasons, I cannot give you the exact dimensions of the device, but I can say that we are really pushing the technology at its limits, and for some characteristics of my device, I even have to violate the design rules of ST for client devices design.
So tiny.
Yeah, it's very, very tiny.
But I'm curious also the other way, on the other direction, how many of these devices can you put together for a complete system? I mean,
ideally, or actually,
let's say ideally.
Ideally, we need thousands, millions of qubits to make a quantum computer. But right now, the state of the art in silicon spin qubits, it's 4 qubits coupled together.
Okay.
But we can see that if we indeed manage to harness the advantages of microelectronics industry, it can go up exponentially, because we already have all the silicon foundries, we already have all the techniques, all the knowledge that we need.
So this would be part of your goals to reach a larger number? Or not necessarily?
Yeah, maybe.
Great, and good luck. I would really like to see the results of this research further on. Are there any more questions for you, Ioanna?
Yes, it's Regis. Do you expect in the near future, I would say, to be able to increase the temperature? And if yes, at what level?
I'm not working on this aspect. So at the moment, we work with a dilution refrigerator with a base temperature of 20 millikelvin, and with a variable temperature insert cryostat with a base temperature of 1.5 Kelvin, but this is more like an exploration before putting the device in the dilution refrigerator. But to answer to your question, no, we are not focusing on increasing the temperature.
Okay, thank you.
Welcome.
So maybe I have a question which follow this one. Maybe it's not in your scope, but did you have some work which investigate how the qubit will be controlled by an external electronic? Because at some point we need to have an outside qubit will be an accelerator. So you need to connect your quantum computing to a classical computer. So where is the relationship, and what kind of system you could imagine at system level?
First of all, I would like to clarify that I don't have a qubit right now. I'm working with a quantum dot device, and I want to have quantum dots with no defects that I can control. We work on a project of integration, as you said, and I collaborate with my colleague Ryan Foot at Institut Quantique, who works on capacitance bridge. And we have indeed designed a integrated device for this purpose. And Ryan is working on the improvement of this capacitance bridge right now. And on the third generation of the devices, we will have an updated version of this integrated device. Because as you said, it is indeed a problem to interface qubits that are almost isolated. They can never be entirely isolated because we want to interact with them, but they are at deep cryogenic temperatures and they are isolated from the environment. And we try to interface them with their control electronics, which is outside of the fridge at room temperature. We use so much wiring and so many apparatus that it will become a huge problem in the future if we have thousands of qubits. It could take, people say it could take an entirely football field to put all these things that we need.
Thank you very much. Again, for Ioanna, also, if you still have questions, please use the chat to discuss. And I propose we take a 10-minute break and then meet again at 3:50 to continue with the presentations.
Okay, thank you very much. Bye.